before we try to design drive circuits for practical BJTs and MOSFETs, let us try to understand what an ideal switch is. It will give us more insight while designing the drive circuits for practical switches. Now consider a switch like this. It has a pole and it has a throw, and there is a control pin which will control the single pole, single throw switch. Now this, consider it is an ideal switch. Now what is the IV character of an ideal switch? What is the IV static characteristic of an ideal switch? So let us draw the IV characteristic. X-axis is the voltage axis, voltage across the switch, which is VTP, and current through throw and pole, that is ITP. Now for an ideal switch, we would like that when the switch is on, the current to be able to flow both in the positive and also in the negative direction, meaning T to P and P to T also. And during the time when the switch is off, we would like the voltage across the switch that is to be supported by the switch, that it should be capable of supporting both the forward voltage and also the reverse voltage, positive voltage and also the negative voltage. Now this would be the characteristics of an ideal switch, a static characteristic where you have the I axis covering both the positive and the negative currents, the V axis covering both the positive and the negative voltages. Let us now list down the characteristics of the ideal switch. Now let us say in the on state, when the switch is on, as we saw from the static characteristic, we should say that it should allow current to flow from T to P and allow current to flow from P to T also. That is, support both positive and negative switch currents. Next, the zero conduction loss, meaning when the switch is on, there is a current flow, there should not be any I square R loss within the switch, or there should not be any drop across the switch. Only under such conditions will zero conduction loss happen. So let us say one of the character of an ideal switch is that when the switch is on, there is no power loss in it. As a corollary feature, you have zero conduction resistance. So when the switch is on, there is no resistance, the switch resistance is zero, and therefore the drop across the switch is zero, and therefore the conduction loss is also zero. In the off state, when the switch is off, again looking at the characteristic, it has to support voltage. So it should be capable of supporting both positive and negative voltage across the switch. This is one character of the ideal switch. And also, like during the on state, during the off state also, there should be zero off state loss. No leakage currents should be flowing through the switch. And the resistance when the switch is off should be infinite, meaning zero leakage currents flowing through the switch, and also meaning zero losses in the switch. Another important character of an ideal switch is that switching the switch from on state to off state to on state should be instantaneous. It should be in zero time, which is not so in a practical switch, but this is a desirable feature in an ideal switch. This also implies that if it is instantaneous, if this switching on and switching off happens in zero time, it also means that there is no power loss during switching. So zero power loss during switching. So switching transitions happen in a lossless manner. So therefore switching losses are zero. Then this also implies that the drive circuits to drive this control pin of the single pole single throw switch, these drive circuits will have zero drive power requirement. So therefore just only the information signal is sufficient to be given to the C pin to switch the switch on and off. So these are some of the classic features of an ideal switch. However, you should note that none of these features are fully met in a practical switch. As we have seen, even in the static characteristic of BJTs, diodes and MOSFETs, they do not reflect the static characteristics of the ideal switch. So we have to consider the shortcomings in each of the switches and try to design drive circuits which will try to make up for the shortcomings and take it to as good semiconductor switch, electronic switch as possible. We see here the static characteristic of an ideal switch. During the on time, we see that the ideal switch is capable of supporting both positive currents and negative currents to flow through it, throw to pole and pole to throw. And while the switch is off, it can support a positive voltage across the device and also negative voltage across the device. Now, as against this, how does the static characteristic of a practical semiconductor switch appear? Let us take BJT for an example and see how its static characteristic looks like. So let us say this is the symbol of the BJT. We have the collector, this is an NPN BJT, base, emitter, the voltage across the collector and emitter, we will indicate it like this, and the current through the collector IC. Now you can have on the x-axis VCE, voltage drop across collector and emitter of the BJT, and the collector current IC as the current through the switch. So we know that the collector current is unidirectional. It can only flow the positive direction from C to E. There cannot be a current flow from E to C. So this can support only positive direction of current flow when the switch is on. And when the switch is off, the BJT can withstand only positive voltages across collector and emitter, and therefore only this portion of the static characteristic or potential operating points. So this is how a practical switch will look like. Now let us say that there is an operating point here. What does it mean? It is on the x-axis, it is supporting a voltage, current is 0, which means it is in the off state. So when the switch is in the off state, 0 current is flowing and it is supporting some positive voltage across the collector and emitter. Now let us call this as the off state. Now let us take another point on this axis like this as shown. Here there is some finite current for this operating point and the voltage across the switch is 0. What it basically means is that this is the on state and it is supporting a positive current. Now if I have to transition from off state to the on state, one way is to go along this line with 0 current, go along this line with 0 current, then at 0 voltage, go along this line and reach this operating point. Now if you take this route, at every point on this route the power loss is 0. In all these portions of the route current is 0, and then once 0 voltage is reached, in all this portion of the route voltage is 0. So therefore in transiting from the off state to the on state, you do not lose any power. Likewise, while coming back, you also do not lose power if you are using this route. So in this route, you have 0 switching losses. So which basically means that if I am using a switching with 0 voltage and 0 current, then you have zero switching losses. On the other hand, the practical switches try to reach the other state directly, crossing through the linear region. So when you cross through the linear region, there is finite voltages and current in between, and there will be loss in the device. So these are called the switching losses, and the device should dissipate them through heat sinks and remain cool. However, the efficiency will come down. So this route is a lossy route and lossy transition. We should actually try to avoid that such a route, but all practical semiconductor devices do have this. They directly go through the linear region to reach the other state and back again through the linear region to reach the off state. We should try to make this as quick as possible to reduce the switching losses, or we try to put additional circuit such that it doesn't go through the linear region but goes through this route. So let us design the drive circuits keeping this kind of a background in mind. In order to design drive circuits, just the static characteristic is not sufficient. We need to understand the dynamic behavior of the switch. So let me now write down an NPN BJT switch like this. It's an NPN BJT switch. Voltage across collector and emitter, let me indicate like this. This is collector, the base and the emitter. The collector current flows in this fashion, and there is a base current here. So the base current here initiates the triggering of the switch to turn it on or off. So base current is the control signal or the trigger signal. So now let us divide the time into 4 parts. So let me make the division. So let us say here first the transistor was off, and then there is a portion of time here off to on. This is switch on of the transistor. Then there is the on state of the BJT. And then there is an on to off or switch off of the BJT. Back to the off state. So the cycle repeats. So this time period is the turn on time period. And this time period is called the turn off time period. So in order to understand the switching behavior of the switch, let us try to look a bit more in depth into these parts, the turn on part, and this part, the turn off part, in a bit more detail. So let me first take this turn on part and let me zoom it. So I'm going to plot 4 waveforms on this. Okay, let me tell you what they are going to be. So first, this is called the turn on time. Now here it was off state, so the switch was off and there was a positive voltage VCE which was being withstood, supported by the off switch, and there is a 0 base current here. Okay, at this point, at this instant, I am initiating a base current to flow through this device here. So let's say the base current has a finite rise time and then moves in this fashion, and that is called IB. Now because of this IB, the VC which was here tends to drop like this in this fashion. Now this is called VCE. And what happens to the collector? As the VCE is dropping, the collector current is increasing. So the collector current increases, and during the turn on time it increases more than what is required and then comes down to whatever is dictated by the load. Now if I multiply instantaneously VCE into IC, I will get here the instantaneous power curve during the turn on period. So this is multiplication of IC into VCE. The instantaneous value of IC and VCE, instantaneous value and VCE, keep on multiplying and then plot this curve. So this looks like this. Now let us say this. Now relative to this IB, let me make few changes so that you try to get some more insight. So next, I will place another similar segment, turn on segment, and let us view the same waveforms. Now IB, I slightly increase. I give a higher value of IB. If I give a higher value of IB, what happens? What happens to the VCE waveform? VCE was off here, call that VCE, and how does it evolve? So you will see that it goes much more smoothly and quicker towards the on state. And you will see a slight rise in the collector during the turn on period, and then again it comes back and settles at the same value, which is then later controlled by the external load. Now this is IC. Now what is IC into VCE looking like during this period here? So you see that there is, because VCE drops quickly, there is a drop here, and then the height is reduced, and this is the IC into VCE, the instantaneous power curve. You will see that it has reduced significantly. Now I will make one more change to the turn on base current. I am going to give a base current in this fashion. I give a kind of a small surge base current during the turn on, and then bring it back down to the normal operating base current. Now this turn on surge base current will make the VCE to go down much faster. It will go into the on state much quicker, and then there will be an IC which goes high and then comes back to the normal operating IC. What happens to the power curve? So you see that during the time when IC is large, VC has already reached the on state. So most of the power dissipation will be in this zone. So you will see that there is a peaking of the power dissipation IC into VCE curve, and then goes down quickly. So you see that the power dissipation is much reduced in this case. So typically we would like to give here the base current with a turn on surge current which is higher than the normal operating base current. So you give a turn on surge current and then let it settle down to the normal operating base current. You will get the best switching speeds, and not only that, the power dissipation is lower. Now what happens during turn off? So during turn off, I am going to focus here on this portion. You are going from the on state to the off state. Now let me let's see the same waveforms, how it looks in the turn off condition. Now I'm going to split the turn off into two zones here. I will explain what that zones is. It will become evident the moment you look at the waveforms. So now look at the base current. The base current was at this level, and then I'm going to initiate turn off of the base current. So let the base current be turned off. So base current is turned off. Actually you are removing the base drive, but the base current here then starts going negative, means there is some base charge which is removed from the base of the transistor. Remember that the BJT is a semiconductor device, and there is some base charge which is stored in the base capacitor of the transistor, and that has to be released, and that has to flow out in the negative direction. So that is this negative base current, and then as the base charge gets removed, you will see that the base current finally dies down to zero. So even though you have initiated removal of the base current here, you have stopped the base drive here, it takes some time for the base charge to recombine, and this is the area under this curve is the base charge that has been removed, and that takes a finite time. Now this is base current, and now if you look at the collector current actually you see that stays almost unchanged till this vertical line that I have drawn, and then it starts to decrease and then go to 0 into the off state. So this period where nothing much happens in the collector current or even in the collector to emitter voltage, this period is called the storage period. So this is called the storage period because most of the base charge is in the process of getting removed. So majority of the base charge will get removed up to this period, and then only later, when there is only a small amount of base charge removed, this actually shows a trend towards switch off. Likewise, if I look at the VCE waveform, nothing much happens up to the storage period. Looks as though the transistor is still continuing to be in the on state. Then when majority of the base charge is removed here, you will see that the voltage starts to increase and then starts to support the forward voltage. What about the power curve? Even in the power curve here, during this period, VC is 0, not much of power dissipation there. So if I take IC into VCE here, there is only a slight increase there is a slight power dissipation, and the majority of the power dissipation happens here when it is passing through the active region. So this moves in this fashion. So this is the IC into VCE curve, and this is actually the turn-off loss, instantaneous value of the turn-off loss. So our job is to keep during turn-on this portion as small as possible by providing a turn-on surge base current and then allowing it to settle to the nominal base current. And during turn-off, we need to provide path for the base current to reverse so that the base charges of the BJT are removed. And during first portion of the turn-off period, which we call as TS or the storage period, you will not see much change in IC and VC because the base charges are in the process of getting removed, and majority will get removed at the end of storage time. Further on, the remaining time is called the TF or fall time, and that is when the current is actually falling down to 0 and VC is rising to block the forward voltage, and that is when actually majority of the turn-off switching loss occurs, and we need to keep that one to a minimum. So the nature of the base drive that we have to give, look at this. This is the turn-off portion. You give a surge base drive for on, and then you will have to have an on state base current, and then while turning off, we'll have to have facility for negative base current so that there is a possibility of current flowing in the negative direction and sinking somewhere. Only then the base charges can be removed. So if we give a base drive for the BJT where the currents are of this form, of this shape, then you will be actually generating a proper base drive for the BJT. So keeping this background in mind, let us design some base drives for the BJT. Now we can summarize the BJT base drive requirement. So base drive for the BJT means base current, and how should be a typical base current be for switching on and switching off the BJT device. So let us say the base current during the off state, the base current is 0, and during the turn on portion you give a base current surge, and then it will settle to a lower value which will be the normal on base drive. So this we saw will reduce the power dissipation, turn on power dissipation, and then you keep it continuously on such that the BJT is in the on state. You have to give a value of IB greater than IC by HF SAT or IC by beta, and then during the time when you want to turn off, you need to make it go negative. Possibility for sinking capability of the base drive circuit should have sinking capability, and then it will settle and go back to 0 in the off state. So this will be the typical base drive current wave shape that will be required for BJT, switching BJT. Now let us mark this peak value, we will call it as IB plus, and this normally on value we'll call it as IB on, and this negative base current peak value we'll call it as IB minus. So we'll use these symbols, labels, so that consistently we know what we mean, and we can visualize when we use these IB plus, IB on and IB minus symbols. So IB on is the normal on state of the BJT switch, which means you will be providing at least greater than IC by HFE SAT. So normally IB on we will give 2 times IC by HFE SAT. So when you give 2 times IC by HFE SAT, it is going to drive the transistor into saturation. So you are sure that the transistor, the BJT, is going to be in saturation. So this is a thumb rule that normally designers follow. 2 IC by HFE SAT, good starting value to use. Then IB plus, the turn on surge, that magnitude value will be 1.5 to 2 times IB on. And IB minus, the turn off negative magnitude is 1.5 times IB on in magnitude. Now these are typical design guidelines. There is no formula for this. These are thumb rules, empirical by in nature. So these have worked for many designers all over the world. So it's a good starting value. You start with this design and then fine tune it from there on. So let us now draw our first base drive circuit. So this base drive circuit that we are going to draw now will be the basic building block of most base drive circuit, very important and very popular. So it is very simple. It consists of this transistor. This is the transistor BJT that needs to be switched on and off. It consists of just 2 components for driving the drive circuit. It has a one resistor and another resistor like this, connected in this fashion. So this BJT is the BJT to be operated, and these two are the drive circuits. So you give a base signal here, and the currents are limited by this R1 and R2. So there is this current IC which is decided by the external load, and here you have to give IB on to turn on the BJT to full on condition. We'll call this one as R1 and this one as R2. And the character of this BJT, after you have selected, you will know from the data sheet what is HFE SAT value, or it is also sometimes called the beta value. This is VBE SAT. So when the BJT is on, is a saturated condition, the base emitter voltage is called VBE SAT. It will be around 0.7 volts. So now let us design the value of R2. R2 is, we know the voltage across R2 is VBE SAT. So VBE SAT divided by how much current will one allow through R2. Normally a current equivalent of IB on will be allowed through R2. So I will say IB on. So this will be VB SAT by IB on. And what is IB on? IB on is 2 times IC by HFE SAT, 2 times IC by HFE SAT. And therefore we can say VB SAT into HFE SAT by 2 times IC will be the equation that one can use for choosing R2. You can also choose the power rating of R2 because you know the current that is going to flow through that. IB on, IB on into root of the duty cycle will give the RMS current, and thereby you can find the IRMS square into R, power dissipation of the resistor. Now how to find the value of R1? So there is a drive signal VB, let us say, coming here, and we will name it as VB. Now what is the voltage drop across R1? VB minus VB SAT. This is VB SAT potential. So VB minus VB SAT is the voltage drop across R, divided by R1 will be the current through it. What is the current through it? There is IB on flowing through R2. There is IB on flowing through into the base of the BJT. So 2 IB on will be flowing in R1. So 2 times IB on. And IB on itself we know is 2 IC by HFE SAT. So VB SAT into VB minus VB SAT and HFE SAT divided by 4 times IC. So this will be the equation to select R1. For this circuit, let us see how the dynamic characteristic look like. So let us plot against time t. This is the off state, on state. You have the turn on, you have the turn off, and this is the off state. So during the off state, IB is 0. So that is the current here is 0. And during the time when you want to turn it on, the on state, IB on, this is IB on. However, there is no special arrangement in the circuit to provide a turn on surge. It will just go and stick to IB on right even during turn on. And during turn off, because of R2, there is a path for reverse current to flow here so that the base charges recombine. So we have a negative base current flowing in this fashion. So this value is VB SAT divided by R2, current will be flowing through that, and here it is IB on. So this is how the drive currents will look like for a circuit of this type. There is no speed up, but otherwise you have other aspects of the drive current requirements being met. So this is a very simple base drive circuit, and it is a building block for many other complex base drive circuits, which we will see later.